realizing on your printed program that I will talk about finite groups Lie type is just a bit vague. So what I will actually do is I will chat about exceptional finite groups of Lie type and their primitive actions. It's a chat because I entered this world only very recently, about 10 months ago. And before that, I was doing something related to construction and identification of small groups, finite groups. So yeah, it's going to be a chat. And also thanks to...
Oh no, not again. Do it again? Okay, yeah.
Oh, okay. Thanks to all the speakers before me, you've heard everything you need. And it's great because it motivates my talk, so this will be really just a chat. So for example, yesterday we've seen so many primitive group actions, and today we've had the nice setup of algebraic groups and then the finite version and everything basically. So what I'm gonna do, oops, too many slides, is I will look at primitive group actions of finite groups Lie type. But before that, I'll just kind of still motivate a bit, because when we look at any transitive group actions, not just the primitive ones, generally it's a good question to ask, like, can we find the subdegrees of these kind of actions? And if you need a little reminder what subdegrees are, well, you take a point stabilizer when you have a transitive action, and you look at the orbits of those point stabilizers, and they're called the suborbits, makes sense. And the sizes of those suborbits are called the subdegrees. Okay, so example. So if you have a group, well, I only care about finite groups. My whole life so far, only finite. And you take a subgroup, and naturally you have a transitive action, you know, on the cosets, right? And Connie yesterday told us that this action is primitive, even only if your subgroup is maximal. Okay, so, and not sure if that makes Rebecca happy. Our point stabilizer happens to be H. And now, thanks to the orbit stabilizer theorem, it tells us exactly how to calculate the subdegrees, because the size of the orbit, so really you just do your size of your group and divide it by the stabilizer. And here we have already started with the point stabilizer, so the, you just divide it by the size of the 2-point stabilizer. That's straightforward. And then I will look at finite groups of Lie type, and we have so many viewpoints of these kind of groups. So what I look at will be the viewpoint 3. So we look at them as fixed point subgroups of algebraic groups. And a slightly less vague description of that. So we know, also heard today, that all those linear algebraic groups can be embedded into GRN. So it's naturally that we start with GRN. And the Frobenius map, you've also seen it. So you just really take a matrix and map each entry to its power of q. And if that q is the prime power of your underlying characteristic, then you get a non-trivial fixed point subgroup. And here we get GRNQ. And of course, we can do the same game with other algebraic groups, right? Because they're all just closed subgroups of GRN. And we can also generalize this map to this Steinberg endomorphism. So an example we've seen at least twice today is the transpose inverse. So the generalization is really just if you have this kind of map and you iterate it multiple times, you eventually get back to some sort of Frobenius map. Then that's it. And then you take the fixed point subgroup, and that's how I find the groups of Lie type. And also, a nice thing about the Steinberg endomorphism, we've heard all the times, but also I will just refer you to section 22.1 in the nice book written by Donna and Gunther Meller, the Bible. all about the classification of this type endomorphism, they were there. And what we're trying to do then, by now I guess you already don't remember what I set out to do, which is fair, because I also realized only very recently that I've been thinking a different question, slightly less useful and slightly harder. So let's actually start out our question. So we take our exceptional finite groups Lie type. So we've seen a lot of classical ones today, and there are some exceptional ones. And we take a maximal subgroup of that, and we want to determine this primitive coset action, the subdegrees of this primitive coset action. And how? We, again, as we've seen before, we can do this by calculating the intersections of the two-point stabilizer, just the two-point stabilizer. And so this kind of questions has been answered for some groups and for some of their subgroups. For example, Loth and Saxo, there's kind of questions I think out of interest for knowing distance transitive graphs, which I have, like I know nothing about. And Bana and Son and Yamada also did this for G2 acting on the subgroup type A2 extended by involution, because they wanted to determine the character table of the commutative association schemes. I can't even say this word because I really don't know anything about this. And we didn't know of this paper until also very recently, so because it's not very easy to tell that what we want is hidden in some paper like this. So if you happen to know anything about this and you have some time to spare, you can tell me why I do is useful. Or if you have encountered any paper that also happens to calculate the subdegrees of exceptional finite group Lie types, you can also let me know. That would be great. Okay, so but we thought that this would be a good starting point because they did it in a way that's sort of very different from Loth's approach. So we revisited this case, this example, and we sort of used Loth's approach. So how exactly it is? So if you again need a little reminder what G2 is, here's the root diagram. So you have 6 long roots, 6 short roots. They're generated by alpha, beta. Alpha is the short one. Here I used alpha being the short one and beta being the long one. And you have this algorithm called Borel-de-Subenthal's algorithm basically tells you how to find sort of maximal subgroups. Well, subsystems, subgroups, but they help you to find maximal subgroups. So here what we do is we have the extended linking. If that gets complicated, you don't want to hear about it. You just we remove all the short roots, we keep the long roots, and we keep the subgroup generated by still the maximal torus and the root groups by those long roots. And then we get this subgroup of type A2, right? Because if you look at the long roots, this is type A2. And now we take the fixed point subgroups. So upstairs we have G2 over this algebraically closed field. Downstairs we have G2 over Q, right? And correspondingly, this A2 also, you can look at the fixed point subgroup of that Steinberg endomorphism, and we get a subgroup A2 over Q. There are 2 types of A2. You have the unitary, you have the spatial linear. We look at the SL case for now. And it's not maximal yet, but if you take its normalizer in the group, you get actually a maximal subgroup. Okay, so we can now start acting on this, the coset of these maximal subgroups, right? And we, again, if you don't remember what I was trying to do, I want to calculate the subdegrees. And this is the formula for calculating subdegrees. So naturally, I want to calculate the intersections, but also I know these orbits. I one-to-one correspondence with the double coset, which you also just heard about in Aluna's talk. And so upstairs, we have, that's a typo, that G not meant to just be G. So upstairs in the algebraic groups, Aluna would just look at it and say, there are infinitely many of them, no hope. But here in the finite case, everything's finite, so we have the counting argument, right? So we can actually know when exactly we find all of the suborbits. So we know exactly when we can stop finding those subdegrees by looking at just the disjoint double cosets, and when we have enough things to recover G, we're done. Because we use Loth's approach, well, at least it's similar to his approach, it's appropriate to quote him. It's not complicated. And the reason it's complicated is because the theory is very down to earth. We really try to do things by first principles, right? So we really start looking at like the elements and how they act on my H, this maximal subgroup by conjugation, right? And thanks to Donna who mentioned E.Pan. So E.Pan and also Aluna mentioned Burhat decomposition. So this thing gives us a normal form, so you can express elements uniquely So that is quite powerful computationally. So naturally, I also don't be silly. I don't start looking at things that's already in H, which means I already ignore all those things that's generated by long roots, right? So I'll start looking at just the shortest element. It's unipotent root element. Hopefully this still rings a bell from earlier this morning. So alpha is definitely outside of my H, because alpha is a short root, it's outside a group of long roots. And I'll look at how it acts. So along the way, I will use use the Chevrolet's commutator formula, so that helps me to calculate the conjugation. And also I will use some structural results from algebraic groups upstairs, because Land-Sternberg tells me I can do that. And that's why we look at these kind of things from viewpoint 3. So I calculated those intersections. I look at basically I can actually get the isomorphism type of my intersection, and the order will just follow. And then I will just extend the length of my elements, not just one alpha, but I can start what if I multiply 2 short roots, what do I get? And I play the same game. I will do this conjugation and find the intersection. That's all good. You can see from the lens of my description of this kind of representative that it gets harder. So I think the hardest case for me so far is the last one, because so by just playing around in magma, I know kind of what I should look at, because I've already looked at all the positive roots. I should probably also now start considering something semi-simple, or neither semi-simple, neither unipotent. So I will just start multiplying long roots and short roots. But again, root-hard decomposition tells me I can rewrite them all into positive roots, some via element, positive root. So I start playing around with those, and there's this slightly annoying number theory problem I need to solve, because you can see from the half there is some pairing involved. So figuring out that pairing is just, I think it's more or less some number theory kind of problem. Yeah, so that's it. That's how I figured out this whole thing. And with the SU case, the method will be the same, but obviously the calculation will be different, because along the way I will have to really look at how the elements act on my torus. So in the unitary case, that would be different, because the fixed points and my Sternberg isomorphism will be different. So, but that's all work in progress, and that's what I'm going to do for the rest of my PhD, I guess. But also along the way, because I mentioned that I was looking at a question that's slightly different and less useful and slightly harder, because I started out trying to classify all these intersections up to conjugacy. But I mean, they can be distinct cosets, but they might still be conjugate. So along the way, I found okay, there are much fewer conjugacy classes of these intersections, and even amongst those half of Q minus 3 subdegrees, suborbits, or subdegrees, whatever, intersections, I see 2 different isomorphism types appear. So there is this extension problem that can be interesting to solve. I care about extension problem because of my background. So that's something I can do. And also I can try to find the subdegrees of other maximal subgroups, because we do have a whole list of maximal subgroups of exceptional groups, including G2. And actually you can find an explicit list in the book Kova just mentioned, written by John Bray and Derek Holt and Kova herself. It's tables 8.41. It's quite hard. I go there too often. So you have this whole list, you can play the same game, going through each case. But obviously, my method here would not always be, useful. I can play the same game with the other subdegree subgroups, which it will be of type A1. So you will get that from applying the Borel, the Subenthalles algorithm. But you also get weirder groups, exotic groups, and the Yanko group appear. Well, yeah, that's future work. And if I be super ambitious, I can even try to do some of these questions with other exceptional types, not just G2. G2E is quite simple when you look at the roots, right? But I think computationally I can try to implement some results, like the intersections, now I know them. If I can solve the isomorphism problem, it could be nice invariants. Yeah, that's all for my talk. And yeah, I won't take too much time before your lunch, so you can just quickly answer you.